groundbreaking approach for sampling pre-up stages, where time-honored techniques for capturing analog hardware character meet a new generation of technology. The result? An even more faithful recreation of real preamp behavior, even when pushed beyond their limits. In this video, we will dive deeper to see how the best of both worlds combine to create something we've never seen before.
Since its beginnings, Acustica has used a special technology in its object sampling workflow. Across very different hardware, Volterra kernel technology is the method that allows us to obtain a series of results that are then useful for optimization and faithful modeling of the unit in question. It is interesting to see, especially with regard to the harmonics, that here we can see the graph, the graphical representation of a test signal at 1000 Hz. Again, we are in bypass, so this is just the conversion path, just the converters. If I insert the unit, we can immediately see a series of harmonics created by the circuit of this equalizer. In particular, we see the second, the third, the fourth harmonics, and gradually all the others. The interesting thing is that these harmonics are obviously very sensitive depending on the input signal. By increasing the input signal and trying to compensate the output so as not to change the overall level, we can see how the harmonics rise significantly in intensity relative to the fundamental, and by continuing to raise the input level and adjust the output, you see that the harmonics tend to go down. This is behavior that is well represented by Volterra kernel technology, because you can sample these states at different dynamic levels, and then the engine inside the application, essentially, which is an evolution of nebula, for each sample manages to map the right vector and then recreate the behavior. In practice, we can see that it is highly variable depending on the input level at the time of sampling. So it is important to be clear about what strategy to follow and how to separate the various aspects of behavior of the unit that must be sampled. To perform this operation, you usually need to go down to the engine room, when possible, to get inside the machine. Obviously, it is very helpful to be able to consult the electrical schematic of the unit. This is not always available, so in those cases, you have to go a bit by intuition. You have to proceed by identifying the most suitable points to isolate the characteristics of the different behaviors of the machine.
So we started out as Acustica audio neural network models in 2022 with a product called Aero, which is aimed at guitar distortion. NAM models, Neural Amp Modeler, or other WaveNet-based models are very effective when we are dealing with distortion, very strong saturation, and that is why we started using them. At the time, we were hoping to be able to integrate this kind of technology into our traditional processors, but we quickly realized that it did not have the precision required. And a second problem was that the models were too heavy in terms of CPU consumption. On this second point, we worked extensively with neural networks and agents, in this case, to rewrite WaveNet code. Just to give an example, our executable now consumes only 1/3 of what an average plugin would use when running these models on the CPU. The problem we used to see, however, was that despite the lower consumption, these models also tend to be very inaccurate. And that is why, in the end, we decided to abandon them, or at least find a strategy to limit their use only to cases where saturation is very evident. In fact, these models are very good when saturation is very strong, and they are also very gradual. They have many advantages, and these are linked to a parameter called dilation, which explains what their quality is. The problem arises when we have to use them to reproduce high-precision machines, like those normally used for mastering, especially in the range where these machines are used, and certainly not with the intention of heavy distortion.
Quello di una distorsione spinta. Parliamo brevemente del gain staging.
Let's briefly talk about gain staging. With regard to the Volterra model, over time, we have always sampled at much lower levels than were possible. For example, our sampling equipment goes up to more than plus 23 dBV, but at those levels, Volterra only gives junk. It only produces garbage, and that is why we usually sample from minus 18 dB, going downward to represent all the underlying dynamic levels. Now, what is the problem? The part that goes from 0 upward, we have to try to imagine, because we cannot sample it. Over time, we refine techniques based heavily on wave shaping and anti-aliasing techniques that allow us to reproduce, to some extent, the saturation curve these units have in this dynamic range. However, it is never a faithful reproduction, even though we are able to project the Volterra kernels to higher levels as well. On the other hand, the WaveNet system, Neural Amp Modeler, or Guitar ML type systems, have the advantage of being much more gradual, and when we sample them, to make it clear, we do so between about minus 12 and 0, where we said that 0 corresponds to roughly plus 23 dBV. In this range, these models still behave convincingly, and then we use these models to reproduce all the higher dynamic levels. At that point, the behavior becomes much more gradual, and we are able to reproduce, in a way that is much more effective, the part where the unit is saturating significantly.
Achieving this result took an enormous effort, AI technologies and advanced analysis tools, but above all, a long process of critical listening, because every preamp generates its own emotion, a unique balance of harmonics, a special way of making every frequency vibrate.
We talked it over and said, what if we combined these two models? That is, if on one side we had Volterra working up to a certain level, because it is very good there, and then above that level we brought in NAM and combined the models, we could obtain a kind of macro model that in artificial intelligence is called a mixture of experts, that is, the best of both worlds. It is as if we had an expert in low dynamic levels doing that job well, and then above that level, another one doing the heavy lifting. I would now like to show it over there, and in my opinion, this is something truly innovative. In the end, it's obvious in hindsight.
Let's head down to the laboratory, because the way a circuit is sampled can deeply influence the final result. It's not just capturing a snapshot, it's about understanding the entire circuit behavior, chasing those traits and make it truly unique and musical.
In this case, we are sampling the preamp section, that is, the nonlinear part, the one that creates the color of the sound, and the harmonics. Here, we are absolutely not interested in sampling the static equalization section. To do this, you need to go inside the machine and inject the signal, picking it up from specific points, targeting the part of the circuit we want to sample, while excluding everything else. Once the best points have been found, to obtain the result we are aiming for, sampling is carried out with a series of test tones, which are essentially sweeps, used to capture the behavior of the machine at different levels, and therefore with all the harmonic variations that the machine generates as dynamics change. And this is then reproduced in real time by the Acustica engine, which recreates over time the generation of these harmonics, varying according to the level of the input signal.
To show what this really means in practice, Stefano and Giancarlo will guide us right into the heart of this process.
One of Volterra's limitations is gradualness, and you can see how, although it obviously makes microprogram, once it stabilizes, it is fine. You can see that they increase very gradually. Now we are increasing the input level, because NAM is coming into play here, helping it. In fact, you can also see it from the number of harmonics. It is already producing many more. Let's move on again, and it manages to remain absolutely gradual. The transition from one to the other is preserved and perfect. So the two models, from the point of view of harmonic distortion, communicate. Let us go back for a moment and look at the response in frequency, and that is a beautiful thing. If I look at the frequency response, it is beautiful. That is, the appearance is what we have always had in Acustica, and this also corresponds to a beautiful transient response. And when I raise it, you can see that I move into the NAM area. It breaks, but the Volterra part saves it compared to what it would normally do. So even when I saturate it heavily, it continues to remain what we expect from the machine and not a broken object, because it is still being helped. Now let us push it much harder and see it break, but it is still correct. It is only at the very end, clearly, that we enter a zone where it is completely broken. I think this is an exceptional result. The phase is beautiful. Show the phase, because that too is important. Look at the phase. The phase is perfect. The machine has this particular phase curve due to the transformers, and you can see that the phase is perfect. So the transition from one model to the other helps it, and it does so dynamically over time. And even when it is completely broken, the signature is still there.
L'impronta è sempre quella lì.
Nova technology makes a major milestone, a new standard for sampling and reconstructing preamp stage behaviors. These subtle details that profoundly shape the character of every analog unit. From here emerged a new generation of digital tools, capable of delivering all the complexity and musicality of the original hardware.